Welcome back to the third video in our little series about numerical simulations. Today we're gonna take a look at partial differential equations. You can already see the heat equation in the background as a prime example for this type of equations. Here, the hills and the valleys of course describe areas of warm and cold temperature. And you'll see that if you understand the motion of these waves here, it's not a big jump anymore to get to some quantum mechanics. But let's take it one step after another. In the previous episodes, we dealt with ordinary differential equations. So systems that can be described by an expression like this, where the second derivative, or acceleration, is a function of the velocity and position. This already brought us some very pretty animations, like this Lorentz attractor here. Others we even made interactable in the last video, and we'll be relying on some of the things we used there. But if we want to move on to partial differential equations, we have to understand a very important property all of these systems share. They depend on a single variable. Take this pendulum as an example. Even though it is a two-dimensional object, the angle describes each position uniquely. And the angle in turn only depends on time. So if we know the time, we know the position. Then it makes sense that this function can only contain time derivatives. But for a moment, I want you to try and think of a system that we can't describe like this. Now, based on what you already saw, and given the title of this video, I think you see where I'm getting at. A prominent example would be temperature. As you watch the coffee being poured, you can see the temperature of the mug changing. So again, we have a time dependency. But if I overlay a grid here, we can see that the temperature is also different in each grid point. So if we want to describe the temperature distribution in this room, we would need more than one variable. In this case, also an x and a y component for the space. What makes this problem so interesting is that we have two types of variables. In this case, a time component to be able to describe motion, otherwise this whole thing would be a bit trivial, and two spatial ones to specify what point in the image we're talking about. And with this new class of multivariable systems comes a whole new class of differential equations. The most prominent one being the heat equation, of course. To avoid confusion between the time t and the temperature, I'm not gonna call it capital T, but write it as U instead. Also, for simplicity, we'll stick with one spatial dimension for now. The left side of the equation looks similar to what we had before, so the derivative of the temperature with respect to time. But on the right side, we now have a second derivative with respect to x. How I like to think of this equation is by viewing the x-coordinate as a grid. Here it's a bit simpler to describe the effect of the second derivative. Right now we have, say, this distribution of temperatures. How the temperature of a grid point will look at the next moment in time is loosely said given by how much its temperature differs from those of its neighbors. Here we can see its neighbors are hot, while our tile is cold. So if we move the time a short amount, you will see its temperature changed a lot, while the rest of the tiles didn't change much because they were all more or less at a similar temperature. So how can we compute this change in temperature with a solver? Preferably even something similar to the ones from our previous videos. We'll again start with an initial value, so in this case a given temperature distribution like this. And we might as well keep the grid, since we'll have to discretize for the computer anyway. Again, let's just focus on this grid point at index 4. We can discretize the second derivative by only looking at the neighboring cells. As expected, we see the differences between the left and the right neighbor coming into effect here. If we do this for every grid point, we've effectively turned our function u of t and x into a vector of discrete functions of time. Makes sense. If we fix the point in space, the temperature of that point only depends on time. So each component's time derivative is only dependent on its current neighbors. Or in more general cases, on every other grid point. You might recognize this as the coupled system of ordinary equations that we already dealt with in the very first video. So we already know how to solve this problem. Here I've quickly written up a simple simulation using the solver we wrote in that video. To give us some intuition on this heat dissipation, let's just plot the temperature on this axis here and run the solver. We can also tilt our view a bit and see the time component a bit better. Because we constrain ourselves to grid points, we're only simulating these lines here. So this method is very fittingly called the method of lines, and will serve as the primary idea behind solving these equations. Similar to what the Euler method was in part 1. Before we move on to coding, I do want to mention one more thing. Because of the linear nature of our discretized equation, we can pull out these u values here and write the whole thing as a matrix vector system of equations. This makes our solve steps a bit more elegant, because we can explicitly write this multiplication with the @ symbol acting on numpy arrays. Our functions become much more readable since we constrain ourselves to this matrix vector product. To get this whole thing going, I'll first create an empty window with the Piglet library. Very similar to how we started last episode, so nothing too exciting just yet. I'll make a class for the temperature distribution to have all the functionality in one place. As we discussed before, we'll discretize our x-coordinates and temperatures, and store them in numpy arrays. We'll visualize this initial temperature by more or less just plotting it as a function. So take our y values and map them from the temperature range to the screen dimensions. And I think we're gonna need a few more sampling points than that, so let's increase that number to say 200. I'm also not a fan of this plain white color, so I cooked up this shader here. Effectively what it does is it takes a color scheme from, for example, matplotlib, and implements it as a texture on our graphics card. Then I can color each pixel of this line by passing its y-coordinates into our texture. So higher values are obviously warmer colors, while lower y values turn bluish. To actually bring some life into this simulation, we'll first have to set up our matrix. With SciPy, we can create this giant 200 by 200 matrix with just 2 lines. Next, we'll schedule this function to be called by our program 60 times a second. And in here, we'll add our simulation step. Some of you might already know this from the previous video, where we did something similar to also simulate in real time. But something tells me this is not how it's supposed to look. The first few frames are fine, but after that it's just chaos. I double-checked our maths and it should be correct, so maybe let's try reducing the time step the simulation takes, and in turn run multiple iterations in between frames. This seems to have fixed things. The movement looks much more natural now. So let's analyze what's going on here. The first thing that you notice is that the temperature is evening out. So warmer places cool down, while colder places get hotter. This exact behavior is because of our boundary conditions. To be able to simulate this properly, I'm keeping the ends here at a constant temperature. So after enough time, the distribution is just a straight line, where every point has the temperature of our boundaries. I made these sliders here to control the temperature of the edges. So let's see what happens if I make the left side warm and the right side cold. The edges almost instantly adjust themselves to this new temperature, while the center stays constant for quite a while. Again, it intuitively makes sense. If you open a window, which I guess depending on the season would correspond to either the hot or the cold edge, it takes a certain amount of time until the center of your room adjusts to this new temperature. And again, if we wait some time, the distribution takes on this linear form. Even though we don't see movement in our simulation, a slope in the temperature gradient, per definition, causes a heat transfer. In this case, the heat flows from the warmer left side to the colder right side. And since the amount of how much heat gets transferred from one point to another is constant, the gradient doesn't change. If we again exit this equilibrium state, we see the gradient is no longer constant. So some points start gaining more heat and others losing it. I also implemented a way for us to draw heat in this simulation with the mouse. With the left button I can make areas warmer and colder with the right one. As always, I encourage you to try this simulation out for yourselves to really get a feeling for the heat equation. For example, you could try and explain why the right distribution cools down so much quicker than the left one, even though it started out hotter. To at least have an intuitive answer, you really don't need to understand the maths of physics behind it. Before we move on to the 1D heat equation, there is something I want to mention about our current way of solving these differential equations. The method of lines is great because it's easy to grasp and we don't need to come up with a fundamentally new system. We just rephrase the problem in a way that it works with the solvers we already understand, which are all explicit methods, by the way. What characterizes these explicit methods is that if you have the current value, you can explicitly calculate the next one. But unfortunately, this also limits its accuracy. As you saw before, when I was first writing the heat equation, we needed a really small time step for things to even work. So for some of the coming animations, I'll be using the Crank-Nicolson method. What we can notice right away with this method is that now all of a sudden the current terms and the next terms are mixed. For linear problems like ours, we can do some maths magic and simplify it to this expression, where A and B are both matrices, and C is a vector. So instead of an explicit expression for u of t plus delta t, we now connect them with this implicit equation, which we first need to solve for our desired u. This makes our predictions much more accurate, so we should get away with a bigger time step. The downside, of course, is that solving this matrix vector equation is computationally quite a bit more expensive than the method of lines. I won't dive much deeper into this method because I don't want to draw out this video endlessly. But if you're interested in learning more about it, I can highly recommend Alexis Espinosa's website here. There you will find slides and even source code for similar animations. These things really helped me out during the development of this code, so go check them out. I stumbled over his work while I was doing research for this video, and I saw this animation he made on Reddit, which we will also try and recreate today. But before we try tackling quantum mechanical phenomena like these, let's try to improve our heat equation first. My goal would be to move the whole thing into 2 dimensions. we can already kinda fake it with our 1D simulation. For this, we just switch our view to look at it from the top. Then we get this gradient line. If we now stretch this line to the top and bottom edge of the screen, we get the illusion of a 2D simulation, even though we're still only calculating for a single dimension. Obviously, I had to bring you how we calculate the vertices for the shader. Instead of connecting the y values to form a graph, we now use the points as the centers for an array of rectangles that we color according to our temperature. I also had to change the shader code to take in a temperature value, since we can't rely on the position of the vertex anymore. Other than that, we're keeping all the functionality, like drawing heat or the edge temperature sliders. As you look at this visualization of the heat equation, you might realize something else. I'll change our color scheme to simply interpolate between two colors. And this almost looks like paint with two different colors mixing. See how the drop of red paint slowly gets eaten up by the yellow surrounding, which in turn becomes a bit darker. This is of course no coincidence. The form we have for our heat equation is just a simplified case for the general diffusion equation. See how if this alpha is not dependent on u or x, we can pull it out of the derivative and end up with our heat equation. So as long as we assume the diffusion coefficient is a constant, we can simulate the system with the heat equation. Now let's properly implement two dimensions. For this, we'll have to restore the heat equation back to how I presented it in the beginning. Again, we'll try to discretize our spatial components. First, we pull out the x component and turn our u into a vector. And we'll do the same for the y component, leaving us with an only time-dependent matrix. The expressions get a bit bloated with all the indices, but just bear with me for a moment. So how do we utilize this matrix in our differential equation? Meaning, how do we discretize the differential operator? Well, an obvious idea would be to again try and write the differential operator as a matrix. Should work just fine in theory, since you can also multiply a matrix with another matrix. As you saw before, I even took the time and wrote the solver for that. This here takes the RK4 method and applies it to a matrix-matrix IVP, just like the one we're trying to formulate. Yeah, maybe I should have double-checked my work first. Turns out, with the rules of matrix multiplication, there is no way to describe this problem as a simple multiplication. But luckily, there is a simple solution for that. We don't use matrices. Instead, we can take the rows of the matrix and kind of rotate them to form a long column vector. It's all gonna get pretty long, so I'll only show 4 entries here. And for this vector, we can actually write the problem as a matrix vector multiplication, just like for the one-dimensional problem. We can even simplify the expressions really elegantly as Schrödinger products. Again, for better visibility, we're only looking at a small 2x2 grid here. But for larger grids, we would replace these matrices with the one-dimensional derivatives we saw before. And the ones are just the identity matrices. This notation intuitively makes sense, because first we only differentiate with respect to x, and then with respect to y. Since we already covered a lot of the basic setup in the one-dimensional simulation, I'll only show the new stuff. Here I set up the matrices for our simulation. As we just talked about, the time evolution matrix that I call the Laplacian here is given by the Schrödinger product of the one-dimensional derivative with an identity matrix. This Laplacian then gets fed into the RK4 solver step, along with our current temperature values. If you notice, I am still using the method of lines here. That is mainly because with this, it's much easier to properly account for non-zero boundary conditions. But of course, it's also possible with the Crank-Nicolson approach. Similarly for the shader, we don't draw these long column-wise rectangles anymore, but instead cover every grid point on the 2D plane. And for those, we fill in small rectangles. If we take a look at it, the behavior of the temperature is pretty similar to the one-dimensional case. Except now it flows in all directions. For the 2D drawing, I am using a Gaussian profile that serves as the weight factor for the heat amount. During development, I also played around with different profiles, but they all gave me some weird artifacts on the edges, so the Gaussian it is. I feel like the equivalent to other diffusions, like fluids, is even more visible in this fully 2D simulation. The only constraint that we have is that because of our simplification, the fluid can't have any inherent velocity. Again, it's a lot of fun to just mess around with this for a while. Believe me, I've worked on this project for the better part of a month now, and I still draw these shapes every time I run the simulation. Just for fun, I also experimented with other color schemes from Matplotlib. It's as simple as changing one line in the code, and some of the results, like the twilight, really look interesting. I think my favorite is still this one, called Inferno. It's probably the one most connotated with heat. That was also the color scheme of the infrared recording from before. But today we'll use it for an entirely different topic. And that is quantum mechanics. Now, I understand that the topic of quantum mechanics might seem a bit daunting at first, especially to someone who might have never heard of it before. But we've already dealt with the hardest part. If you followed along so far on what we did with the heat equation, you should already understand the maths behind it. And the rest, meaning the physical interpretation and intuition, I'll try to sprinkle in whenever it's convenient. A quick Google of the word quantum mechanics will lead us to the Schrödinger equation. This is the fundamental equation describing the motion of quantum mechanical particles. I'll rewrite it in a form that is more familiar to us. There are multiple formulations of quantum mechanics, and this version, in the form of a differential equation, is the one we're going to be using today. Looking at it, I think you will agree it doesn't look completely unfamiliar. Especially if I bring over these constants to the right hand side and compress them into a variable omega. Then it looks just like our heat equation. So whatever this equation describes, it should behave pretty much like our simulations from before. The only real difference is that our dissipation coefficient is a complex number now, since we're hiding the imaginary unit I in the omega. But luckily that burden gets carried by our libraries, since I can just set the matrices to be complex, and the rest of our code works just fine. I know this sounds a bit unorthodox, but I would really like to try and simulate it first, before explaining it further. Just look at how these animations are similar to what we already know, and how they differ from our expectations. What I've learned during my time at university is that in physics, you don't necessarily need to understand a topic to be able to calculate it. So let's do exactly that. As you can see, for this I am just refactoring our old code a bit and renaming the variables to make sense in this new application. And this is the result. You might recognize this shape as our Gaussian profile from before. Again, without putting too much thought behind it, let's just run the animation and see what happens. So the simulation pretty much looped around once. If we follow it along this time, we see that in the beginning it really does look similar to our heat dissipation. We start with this peak here, and it flows outwards to even out its distribution. This is to be expected, since we again have a second derivative term in our equation that compares the neighboring values, causing most deep areas to flatten out. But when it hits the wall, some weird stuff starts to happen, where it forms these oscillating waves. And no, this time it's not an issue with our simulation step. This really is the motion of this particle. Pretty cool, right? I also thought it would be interesting if I apply both equations to the same initial condition. And here is what it looks like. As long as the wave isn't touching the edges, they look pretty much identical. It's interesting how all this new behavior just comes from the fact that we made our function complex valued. Alright, so what are we even looking at here? Before, the colors showed regions of high and low temperatures. So how can we understand this function psi in a similar context? So far in classical mechanics, we describe bodies by a position. Depending on the dimension, through the variables x, y, and z, for example. This works just fine for stuff like a pendulum. I mean, you can literally see where it is. But this doesn't hold at a smaller scale. So, for example, for atoms. Quantum mechanics tells us that small particles also behave like waves. So we can't say for certain where our body is anymore. While the mass of the pendulum had a clearly defined point, the position of an electron kinda gets blurred. Instead of a position vector x, we use the wave function psi to describe how likely we are to find this electron somewhere. In this regard, it's similar to the temperature. Temperature also doesn't have a single position vector, but rather we're describing how much temperature we have at every point in space. And as silly as it might sound, we're using psi similarly, so to describe how much of an electron we have at every point in space. So what we saw before are the areas in which we're more likely to see our electron, and the areas in which it's probably not to be found. We can still say with some certainty that our electron is located somewhere around here. But if I run the simulation for a bit, we start losing it. Makes sense. If I didn't know where my particle was to start with, and I let it move around for a while, I'll be even less sure of where it is now. Okay, so what about its weird behavior on the edges? Well, you can think of this simulation as our electron being locked into a box. It can move freely inside the box, but it can't leave it. Mathematically, this is achieved by setting boundary conditions. On the edges, the wave function psi has to always be 0, since the probability of finding the particle at, or even past the walls of the box, should always be 0. As our electron is still a particle, we can also give it some other starting conditions. I set up these parameters here to play around with. x0 is its initial position, k0 its initial velocity, and sigma is the spread. So with a lower sigma value, we're more certain where the particle is. Again, I encourage you to play around with them yourselves and see how each parameter affects the result of the simulation. Now let's do something new. We'll introduce an obstacle in our particle's way. So when it's moving from left to right, it will run into this little barrier here. Mathematically, this is described by a potential that we can just tag onto the Schrödinger equation. In our discretized representation, a potential just becomes a diagonal matrix, so it's easy enough to deal with. Again, quantum mechanics undermines our expectations. In classical physics, a particle that has less energy than the potential should just bounce back, like a ball thrown against the wall. In our case, it means that the values of the wave function should all remain zero right of the potential. But here you can see that it not only penetrates the potential, a small portion even makes it through. Most of it gets reflected and changes direction, but we still have non-zero values to the right. This is known as the tunnel effect, in which a quantum mechanical particle can tunnel through a barrier which classically it should not be allowed to pass. It's even more visible if I make the potential a bit thinner. Because of the limited space we're simulating, we're getting these artifacts on the wall collisions. But ignoring that, you definitely see how the wave function also has non-zero probabilities to the right of the wall. The last step now is to move the Schrödinger equation into 2 dimensions as well. But since this doesn't really introduce new physics, and we've already covered the implementation in the code, I think we can skip straight to the animations. We've all earned a bit of a break by now. First, I want to take a look at just a 2D particle being stuck in a box again. This time I didn't make the code interactable, because Python's already struggling to produce these animations as is. Since the whole thing gets a bit dark at times, I'll also include this view. It's the same animation, but the color scheme is dynamically rescaled to the current highest value instead of the starting one. So while the left image shows us the accurate physical probabilities, the right one gives us a better view of what's happening. In total, we get a similar result to the 1D waves, but I think it looks so much cooler in this view. Again, the wave function is leaking out, and through interference, it forms these distinct spots of where the electron can be. So at this time, for example, our electron has to be in one of these 9 peaks. And then, just like in the one-dimensional case, it flows back together to a more localized particle. I'm not entirely sure if there's some special physical effect underlying in this periodicity. So if you happen to have an idea, just leave it in the comments below. We can also put a potential in the box and see how the electron tunnels through it in 2D. As it collides with the wall, we again see reflecting waves forming. Once when it hits the barrier, and once when it hits the wall. For the particle, the wall is just an infinitely high potential that it can't tunnel through. If we look at the bottom animation, we can also clearly see how a portion makes it through the potential. It just stays as a wave packet and moves on. Finally, let's recreate the animation I've shown earlier and send our particle against the Coulomb potential. This is the potential exerted by charged particles. So loosely said, we can see what happens if we send the electron towards another electron. As long as we're far away from the other particle, we're not really feeling an effect. But as we get closer, the repelling force gets stronger as the potential gets steeper. So classically, we would expect our particle to be repelled to the side. Let's see what happens in the simulation. Indeed, the potential curves it away from the center. But since we don't know where the electron is exactly, both paths, up and down, are allowed. What I find interesting is that this area behind the center also gets a marginal probability of finding the electron there. Almost like it tunneled through this other particle, which I guess makes sense since it's still a potential, just like a wall. I think this animation also shows the wall reflections the best. First, the particle breaks up into these distinct waves, that then add back up to a more localized particle. In truth, I wanted to showcase a few more quantum mechanical animations, like a double slit for example. But I am struggling to get them to work, because the time step has to be very small and the resolution high. So I think this is a good place to end the video. I'll probably return to this topic and see how I can improve my code to also run these animations. I understand that this was a very brief excursion into the world of quantum mechanics, and it mostly consisted of me throwing around fancy physics terms, but nonetheless, I hope you take away some insights from this video, and of course that you enjoyed it. I had a lot of fun making this, but after more than a month's time of work, I am ready to move on to other projects. So thank you very much for watching, and see you then.